This seems like a misplaced video. Looks like I've taken you back to the beginning of the term. And a vector between 2 points with an initial point P and a terminal point Q. I just happened to toss them on a line. And we defined our vectors by looking at terminal minus initial displacement of x and y when we were in 2D. So I could represent that vector PQ as delta x, delta y as a vector, and the delta x, delta y is a change in x, comma, change in y. Now there is something else that y'all should remember from your past life that is related to change in x and change in y. Oh, yeah. When it comes to just looking at that line, we used delta y over delta x to represent something we called the slope. Now, if you haven't been thinking about two-dimensional vectors as being related to slopes, surprise! Two-dimensional vectors are related to slopes. There you go. Now, I'm going to do something that's going to seem to come out of nowhere, which is not unusual for me. As long as I have two distinct points on my line, delta x is not going to be 0. And you might be saying, oh, but what if you had a vertical line? I wouldn't be using the word slope on my board if I had a vertical line, because delta x would be 0. So I am clearly, by using the word slope, tossing out vertical lines in the plane. Delta x is a number. So 1 over delta x is a number, which means 1 over delta x is a scalar. And I'm taking a scalar, multiplying it by a vector, which means I multiply each component of that vector by that scalar. And so, look what I get inside of my vector. PQ multiplied by 1 over the change in x. I get 1 comma the slope. I get 1 comma the slope. Oh, and you know what? Because that is just a scalar multiple of my vector PQ, I know that that vector is always parallel to my vector PQ. I know that that vector, as long as I'm not on a vertical line, is always parallel to my vector PQ. That's going to translate into something really important in a little while. Not today, not this week. But it's important enough of a connection to the past that I wanted to bring it into our little ball game. So 1 comma, change in y over change in x, is a vector that is always parallel to a line of slope delta y over delta x. So if I wanted a vector that was parallel to the two-dimensional line y equals 2x plus 3, this vector 1 comma 2 is always parallel to y equals 2x plus 3. Now what I'm about to do may seem totally disconnected. Oh, someday I'll probably say, Hey, remember that time I reminded you that slope can turn into a vector? Maybe I'll remember to link to this video. But since we just went through the process of defining and finding some first partials of some functions of two variables, I wanted to go ahead and introduce this concept of the gradient. Even though we're not going to be using it for anything for a while, I wanted to introduce it now because, well, we can do it now, even if it doesn't have a connotation yet. So the gradient is a vector. The gradient of a two-dimensional function is a very specific vector. It's the vector you get when you use as your x component the partial with respect to x, and as your y component, the partial with respect to y. Now, if we had three independent variables, x, y, and z, we would have a gradient vector with three components, partial with respect to x, partial with respect to y, partial with respect to z. So since you know how to find partial derivatives, you can find these gradient vectors. And again, it seems like I'm pulling it out of absolutely nowhere, and you're probably going, ooh, why did she bring up slope and a vector? Because at some point I'm going to say, recall video, link video. In this video, we discussed gradients aren't hard to find unless the partials are hard to find. And they're just composed of the components you get when you take your first partials and put commas in between them. And you put the partials in the same order as your variables. So if you have a function of xy, then your gradient is also a function of xy. And it is the vector you get from looking at the partial with respect to x, comma, the partial with respect to y, which are also both functions of x and y. Now this notation that looks like an upside down triangle, it might look to you like an upside down delta. It actually is supposed to be kind of flat on one side if we go with traditional notation. I don't care. But the arrow thingy goes over both that upside down triangle and the name of the function. It does not go over the variables. The gradient is a vector valued function. All that stuff we could do with vector valued functions a little while ago, we can do with gradients. Plug stuff in, talk about, special spots, and so on. I'm not going to ask you to do much with gradient. I am going to ask you to do some things that do a little foreshadowing. But since we know how to find first partials now, may as well go ahead and introduce this concept, which I know those of you who want applications and to see where everything is coming from are going, why would this even come from anywhere? You got to trust me. Sometimes you just have to trust me. See you soon.